Hello, this is Paul Craig, and this is the fifth and final prep video for the IQB webinar, or crash course actually, Python for Chem Informatics Driven Molecular Docking. And we're going to be looking today at Pandas and Seaborn and a few other tools. So let's go to share that notebook. Again, this notebook is from the Molecular Science Software Institute, and it was created by Jessica Nash at Molsey. And so in this unit, we're going to be looking at examining and visualizing data using mostly the Pandas and Seaborn libraries. So the questions are, how can I use Pandas to process data? How can I visualize relationships between different parts of my data? And the objective then is to use Pandas and Seaborn to load and explore data. Pandas is a Python library for data analysis and manipulation. And so in data science, it's all over the place. The major data structure of Pandas is called a data frame. A data frame is a 2D array, works closely with NumPy arrays. And where NumPy arrays can work with higher dimensional data, Pandas is strictly two-dimensional, but it is very powerful. And we'll learn how to use it to gather information, to display information. Pandas has many powerful functions built in, including tools that let us avoid having to use for loops and things like that. We can analyze entire columns of data in the data frame at once and generate another column in the data frame based on that analysis. And so for this unit, we'll be using Pandas, the Pandas library, also Seaborn library, Matplotlib, which is also a plotting library, and of course RDKit, which we've been using for a while now. So I'm going to set those up and install those. And as usual, it'll take a few seconds for that to kick in. And now in this case, we have 4 libraries to install, so it could take us a little bit longer. And of course, I can't do anything in the other cells till these libraries are in place. All right, and once again, I notice on the left-hand side here, when there's a check mark, that means that that cell has been completely executed, and at 19 seconds, that's how long it took. And there's no error messages, so we can move forward. So what we're going to do here then is we're going to load a comma-separated file, and that's called a .csv file. It's a simplified version of a spreadsheet, at least on some level. We're going to turn that into a Pandas data frame. In order to do that, in this cell, we'll import Pandas as PD, and PD is the common abbreviation for Pandas. So anytime we want to call a function from Pandas, we just say PD dot and do it. And we're going to use a tool called urllib.request to retrieve some data and put it into a file. All right, and so what's going to happen is the data we're going to download are elements from PubChem. And so when I hit the run cell here, we'll get a data frame. We're calling it df. So df equals PD. So we're calling Pandas. It's going to read CSV of a file name, and the file name is what we've retrieved up here, and it'll turn us into a data frame. So when the cell is complete, we have our data frame. And notice our data frame has columns and rows. So this is all the elements. So from element 1 through element 118. And we have the symbol, the name, the atomic mass, and so on. So there's a lot of descriptors here. We'll actually be adding a few more columns toward the end here as we move through this notebook. Now, Pandas has a bunch of tools that are designed to let us explore the data. So one of the tools is, now our data frame is called df. So df is a Pandas data frame. It's its own entity, and it has methods associated with it. One of the methods is the head method. So when I run this cell, what we see are the first 5 rows of that. Now I can actually put a value in there. I can say, let's see the first 10 rows. And so we see the first 10 rows. And notice once again, this is Pandas. So the first row is number 0 through number 9 is the 10th row. We can also use the df info function. And the info function, so df.info, And that's going to tell us about all of the columns. So here's the data number for the column. Here's what's in that column. It tells us what's the content of that column, what's the data type. So is it an integer? So int64 or float64. So those are numbers. The others are all objects. So they have certain functions that they can do. And so we have all of that information. Another function we can use with data frames is called describe. So with describe, it just will take each of the columns, give us the count of elements in that column. Notice we have 118 elements, 118 have an atomic mass, only 95 have a recorded electronegativity value. And we're listed the mean, standard deviation, the minimum value, 25%, 50%, and 70% value, and max value for those. So it gives us a little bit of a description of the data. And we can also do a histogram. So this is once again a built-in function in data frames. So you don't have to call in a plotting library to do this. You just say df, that's our data frame, dot hist, and it tells us to have a figure of this size, and the edge color is going to be black, and there won't be a grid in it. So notice that first we saw this information pop up, and then eventually we get a graph, and that graph shows us basically different numbers as they go through the different parts of the periodic table. Now, we can access the data in a Pandas data frame in a number of ways. We can access rows and columns. And so first of all, we want to know the number of rows and the number of columns. And that's where we use the shape function for the data frame. When we do that, we find that we have 118 rows and 17 columns. Now, if you want to come back and want to check that again and you don't remember where this cell is, you just hit the variables tool here on the side. It populates with all the variables that have been declared. And if we look at the row for DF, it tells us it's a data frame. The shape is 118 rows by 17 columns. And then it tells us what the different rows are. And we're not going to keep that open. We just want to remind you that's there. Now, in our data frame, the first column is the atomic number. And so what we can do is we can look at the information in just one column in the data frame. So notice we've got DF, then a square bracket, then the title of the column, atomic number, that's in quotes, a closed square bracket, dot head, and then parentheses. So when I execute that, we just see the results from that one column. All right. You could also go in and say, well, we want to see just two columns from this data frame. So we've got DF, we have a square bracket on the outside, and then another square bracket on the inside with symbol in quotes, comma, electron configuration in quotes, dot head. When we do that, you can see the list of those two columns. And we see the first 5 rows of those two columns. Now we can increase this, and let's say we want to see the first 20. So we just hit that, and it just does the first 20. And you can see it gives us this lovely electron configuration. We can also use Pandas for calculations. So we can do a calculation on all the elements in a particular column. So for example, if we want to convert all of the melting points from Kelvin to Celsius, we have DF and then melting point here in quotes, minus 273.15. When we do that, we get a melting point that's shown here. Notice that some of these NaN means not a number. Okay, so there's no recorded melting point for elements 113 through 117. We could actually do this with two columns as well. And so here we have once again DF. Now, if we have two columns, we need an outside bracket, two square brackets on the outside. And we're going to subtract 273.15 from each column. When we do that, this is what we see. Now, you've probably noticed in this notebook, we're mostly just going to be running the cells. We'll be putting in a little bit of information, but it's mostly a matter of getting accustomed to what Pandas and Seaborn can do. Now, we can actually not just do these calculations, but we can actually go in and add new columns to our data frame. And so we can say DF, and then double square brackets, melting point C, boiling point C. So those are going to be two new columns, equals DF, melting point, comma, boiling point, minus 273.15. Then we'll see the DF head. So when we do that, we scroll over And we can see here's our melting point and boiling point in Kelvin. Go all the way to the right, here's the melting point and boiling point in Celsius. Another very, well, a really nice trick with these data frames is we can use something called the dot apply method. So we can apply a function along a row or a column of a data frame. So for example, if we wanted to know the number of letters and the name for each element, we could say df name in quotes dot apply len, and so it's going to calculate the length. So when we do that, we can see our first element is hydrogen, hydrogen. So that's 8 letters, helium 6 letters, and so forth. And it does that for all of the elements. Now we could add this as a column to our data frame, but we won't. Now we can also use RDKit functions within Pandas data frames. So what we're going to do here, first of all, is we're going to import chem from RDKit. And we're going to initialize a periodic table. And so this is going to be an RDKit object that we can use and we can pull information from. And so that very, very quickly was completed. And so now what we're going to do is we're going to say df outer. So we're going to add another column to the data frame n outer, which is the number of outer shell electrons, equals df symbol dot apply periodic table dot get n outer electrons or outer elects. And when we do that, you can see we've got our atomic number here and so forth. We go all the way to the right, and n outer gives us the number of outer electrons. So we have 1 electron in the outer shell for hydrogen, 2 for helium. We have 1 for lithium, 2 for beryllium, 3 for boron, and so forth. All right, so that exists now, and our data frame contains that information. So what we're going to do now is we're going to use, it says here, use the tab key, but actually Colab is going to show us what we need. What we're going to do is we want the default valence. We're going to add a column called default valence to the element. We're going to say df symbol. So the periodic table is looking for the symbol for the element. And then we're going to apply a function here. And so we want default valence. So if I put in, I just put in DE and it says get default valence. Well, that's the function we want. So we got that. Colab was kind enough to provide that for us. Now, what we're going to do here, this is DF, is get in the data frame. iloc enables us to pull up rows. So iloc is going to pull up rows 21 through 31 from the data frame we eventually generate. And so there's our data frame, once again, rows 21 through 30. And if we go to the end of that data frame, we can see the default valence for the elements there. Now, when I look at that, that doesn't look right to me, but I'm not going to worry about that right now. Now, another thing that we can do is we can take all the data we've collected in that data frame and put them in a comma-separated value file that can then be opened by a tool like a spreadsheet. And we're actually not going to come back and use that, but it's there. Another thing that we like to do when we're looking at structures and data is we like to visualize what we're seeing. And so here we're going to import a library called Seaborn. And the common abbreviation for Seaborn is SNS. And so people often use that. I'm not sure where that started, but that's what's used. And also there's a part of matplotlib called pyplot. So it's very common to have import matplotlib.pyplot as PLT. And once again, that's common usage. So those libraries are now imported. We can use them. And so in the next cell, we're going to use Seaborn to do a plot of, with the x-axis is going to be the number of outer electrons. The y-axis is going to be ionization energy. And the kind of plot is going to be a bar plot. All right. And we're going to rotate the axes labels just a little bit. And so plt.xticks, that's from matplotlib.pyplot, enables us to rotate those axes. So when we do that, we get a nice plot. All right. And so here we see the ionization energy versus the number of outer electrons. that we see for different elements. Do another plot here. I'm going to do a scatter plot this time. So SNS, that's Seaborn, scatter plot. And it says the data, oh, it's in our data frame. Okay. And we're going to use the X is going to be the atomic radius, which is one of the columns in the data frame. Y is going to be electronegativity, which is another column in the data frame. And Q equals group block is going to give us a coloring pattern. Our plot.title, so plt.title. So matplotlib.pyplots enabling us to do this. So here's our plot title, will show up on the top. And we have an X label and a Y label. And it takes a couple minutes to do that. But here's our plot of electronegativity versus atomic radius. And we have a group blocks that tells us what color is associated with which of these spots. I'm going to do a few more plots here. And so the first plot is we want to do a plot of electronegativity versus group block. So the dependent variable is always listed first when we describe these. So electronegativity is going to be the Y value. So that's actually electronegativity. Not sure why Colab isn't suggesting and being helpful there. But then we put group block in for the X value. Once again, we have to tell them the data is coming from our data frame. And we're just going to do a plot like we did before with a title, an X and a Y label. And it takes a little bit of time for that plot to come up. So this took, oh, it says it took 0 seconds. So it took less than half a second. So that's our first plot that was requested. The second one is to say, let's do melting point versus group block. So group block, once again, is going to be the melting point is going to be the Y. We put that information in there, and the rest of the information is like we saw in the previous cell. Execute it. Let me get another plot of the melting point versus the group block. And so we can see that the post-transition metals have the highest melting point, and the noble gases have the lowest melting point. And that's not surprising. And finally, we're going to do one of melting point versus atomic number. So our X is going to be atomic number. And you'll notice that this data frame was set up with convenient and easy to use column titles, which is something you want to do. And so we get another plot like this. Now, in this particular case, we didn't need to rotate the labels on the X-axis, so we just that would do the atomic number there. Now, one of the things we often want to do when we're looking at data is do the correlation between the data in the different columns. All right, so this is going to do a numeric, this command is going to do a correlation, CORR, of our data frame with only numeric values. So if we do that, we can see that atomic number correlates a 1 with atomic number, and it's close to a 1 with atomic mass, but it's not very correlated to things like the melting point. And you can see through the whole table, you could look through the numbers and track them down, but that might get a little tedious. So you can also do something called a heat map. And in a heat map, that heat map is going to take those same data, okay, and we're going to tell it to make a figure of this size. And then we're going to do a heat map using Seaborn. And the heat map, the data is going to come from CORR, which is the variable we defined here. And then we have the annotation is true, and there's cool to warm colors. And the format is 0.2F. So that tells us that any floating point has 2 decimal places. So we get this lovely map, and you can see that as you would expect, the correlation is a 1-to-1 correlation for each column with itself. So atomic number gets a 1 correlation with atomic number. It gets a 1 correlation with atomic mass to 2 decimal places. And you can see here, the warmers are red, the cooler are blue. And so, some correlations are very low, some are very high. And then the final challenge here is just, actually, this is already written out. And so what we're going to do here is we're going to do create a Pandas data frame that contains our structures and shows the molecules. All right, so we're going to import from RDKit, import chem. From RDKit.chem, import descriptors. Import pandas as PD. Now, we already have this in there, so we don't really need to do this. And from RDKit.chem, import panda tools. We do need to do that because that's not in there by default. And then we're going to say Panda tools render images in all data frames, images equal true. This makes sure our little molecules show up as molecules. So we execute that very quickly. There's no output from this cell. So now we need the data that we're going to include in this drawing. And so the data is at a URL, and you can see at the end, it's amino acids.txt. So we're going to retrieve that file. And so we have that file, and it's ready to go. So what we're going to do now is we're actually going to read. Notice the file is called AA file. That's the file name. Okay. And we're going to read those data into actually those data are the amino acids and their SMILES strings. I'm going to read that into a file or into a data structure called AA SMILES. Okay. And then we've created an empty list called AA SMILES underscore strip. And then it's going to go through, and for each SMILES in AA SMILES, it's going to strip that SMILES of unnecessary information and then add that to the end of the list. Then we'll print the whole strip, and then we'll create an amino acid data frame of the SMILES with a SMILES column. And so here we have a listing of all the SMILES strings on the top, and then here's our data frame, and it has 20 rows and 20 SMILES strings there. Now we can actually make RDKit molecules from these SMILES. The way we do this is we're going to add another column to our data frame called molecule equals AADF SMILES dot apply chem.mol from SMILES. So we've seen this before. Okay, so chem.mols from SMILES will just take the information in the SMILES string and generate a molecule. When we do that, we get our data frame, and notice we also get the structures of the molecules. And that's because we activated the Pandas tools earlier. And if we want to, we can actually save the output from this result to a CSV file. And so we're going to say output file equals amino acids underscore process.csv. And then AADF, that's our data frame. We're going to send that to a CSV file called output file. When we execute that, we get our output file. So that's the last of the 5 preparatory notebooks. And hopefully this will prepare you for our Python for cheminformatics driven molecular docking.